Greetings and welcome to a new video. In this video we will discuss the Ziegler Nichols tuning method for the PID controllers. I have discussed this already in another video almost 4 years ago in great detail and used the two methods of the Ziegler Nichols, which is actually a very successful video, so I'm glad that it is helpful for a lot of people. In this case we will also do the digital PID controller design using the Ziegler Nichols method. Of course, I will also show the analog design of that one, so the analog PID controllers will be also discussed, and we will compare that to the digital PID controllers. Of course, we will see also the change in the performance and what kind of effect it has in discretizing our signals. Of course, as we have done it in the previous videos, we will show the calculations step by step and also verify this in the simulations in the MATLAB. And we will see how we can design for a specific situation. So stay tuned now in this example where we see every aspect of the Ziegler Nichols, also the implementation and the realization for analog and the digital PID controllers. So let's see the outline for this video. We have several steps. Actually, I covered this in steps to move in this structured way. What I do first is the first step, look at the unit step response in the open loop system configuration. So we will see shortly what it all means. And we will then determine from there the system parameters. Now you see here a very simple setup. We see here the input signal applied to a plant, which can be anything. And we have this unit step input, and we have the response, which is here an overdamp response. Okay, we see also here in more detail what it all means. So from that, we will determine the DC gain, which is actually this steady state value. Since the input is 1, the KDC is automatically also our DC gain. We also see here the delay, which is the L, time delay. And we also have the time constant T here. Now we will use these three parameters to design the PID controllers shortly. Now from this, we will determine then the analog PID controller transfer function using the Ziegler Nichols table, and for that we of course use these three parameters from step 2. Now the tuning will be done also because this third step will produce an analog PID controller transfer function, and we will verify of course its performance in the closed loop format, but it is not always what we want, so we will like to improve that, and that will be done in step 4. So we will then adjust some parameters in our analog PID controller to get a better performance. It does not mean that we have in the first try already the best option, so we might need another try and then get an option where we say, okay, this is satisfied. Then we will also look at the physical realization of that analog PID control. So once we have a nice transfer function where we can say this is good enough, we can then see how we can realize that using analog components like operational amplifiers, resistors and capacitors. Now, step 6 is then looking at a digital PID controller design. So we will then determine the digital PID controller transfer function, as we have done it actually for step 3, but now in the digital domain. Again, looking at the Ziegler Nichols table, which is of course a different table. We will see that shortly also in more detail. And we will also use the parameters here found in step 2, like a DC gain, the time delay and also time constant. Again, we might need some tuning, so we need to maybe improve the performance of our closed loop system. So in step 7 we'll look at how much improvement we need, and we will also discuss that in great detail. Now also we will implement the PID controller in the digital domain using first we will look at the difference equation, and then we will look at the realization diagram to implement that in any device you want to have for this digital PID controller. Now, final step is very important. We will make a comparison of the final designs of the analog and the digital PID control. So we will see directly what the performance are for both domains. So this is the outline or the steps. So step 1 up to step 9. So we will see how we can do that now. All right. First, before we jump to the steps, let's first discuss what the Ziegler Nichols method are. Now the assumptions and the conditions, first that. Now it is based on an open loop concepts, so relying on the reaction curves. So what I'm now discussing is the first method. It is suitable for a system. It has a large delay time relative to the open loop time constant. What does it mean will be shortly discussed. And it is only used for what we call the first order plus delay time. So it is actually given by this, and it is then for that only applicable. So if you don't have this, this method will not do the job for you. Again, this is the picture we already have seen. The diagram, you see here the response, which is an overdamped response where you see the delay time and also the time constant from a unit step input, and this is the response. So your response must be like that. If it is oscillatory or something like underdamped, you cannot use this method. So the step input can be applied to the process, and it should be also come to a steady state as we have discussed. Now from there, as said, we determine these three parameters, and that will be then used to determine the PID controller. Of course, you can also build a P controller or PI controller. It doesn't mean that you have to do a PID controller, but it is of course up to the PID controller. Now the tuning methods for this Ziegler Nichols steps are the following. Ensure that the process reaches a steady state condition. That is in the practice very important. Apply a unit step input signal for that, and then determine the delay time, time constant, and the DC gain. And from there you can then choose for yourself if you want to design a P controller, PI, or PID controller using the parameters here. Alright, now the procedure. Okay, we obtain that experimentally the response of the plant. So that is most of the time also the case. You don't know the transfer function, you don't know the physics of it, so you have not much information about it. So what you do is you apply to an unknown transfer function. You know the plant, it is in front of you physically. You apply a step input, and then you look at the shape at the output, and it is hopefully like that, and that will then give you an experimentally data. Now from their S-shape, it's called as an S-shape like. It should of course not have an integrator, otherwise you will not have this one. Also not complex conjugate poles, otherwise we get an underdamped oscillatory response. So that is of course not what we need. And if you have that, you can proceed with this method. Now from this, as said, we look at the delay time, time constant, and the DC gain. Now the transfer function we actually look at, G, I call this the plant here. If you don't know, of course, the physics and also don't know the transfer function, you can now from here determine the G, which is the plant transfer function. In this case, you see here the first order system and also the transport lag or the delay time. And that is this part and this part. And now what we do is, in very simple form, you look at the first order system model. This is this one, G1, and the GD is our model for the delay time or the transport lag. And the total transfer function G is just the product of those two, so the G1 and the G2, and that's shown here. And you see also the three parameters again, KDC, the T, and the L. So this is the transfer function you can then develop from this S-shaped measurement. All right. So for the analog PID controller parameters from the table, that is now actually our job now. Now the analog PID controller can be expressed like so. The A stands for analog. You see here the KP, one parameter, TI, which is the integration time, and the TD, which is the derivative time constant. You see it all here. So you can look at a table we will present shortly and then determine these three parameters depending on, of course, your measurement. So the controller parameters are then set according to the formulas, and that is then shown here. So this is the table. If you look, for example, to your T, your L, and the KDC, for example, you measured something, you say, let's say 0.1 second, and then let's say this is 0.5 second, and the KDC is, let's say, 6. You can just put here the numbers and you can make your P, PI, or PID controller, depending on which one you want to design. Okay, let's go down to the step 1 and 2, which is together what we actually cover, which is unit step response of the open loop system, and also determine from there the system parameters. So in this case, we will look at an actual example. So we first covered that in general form what the Ziegler Nichols method is, and I will do that for an actual transfer function. So we have now this transfer function of a plant given G. So in this case the plant is known, so we don't have to know that from the measurement, but it is also possible that you cover this example like you have the transfer function determined from the unit step response on the open loop configuration. That's possible. So I will have now the transfer function already, and we will use the first method of the Ziegler Nichols. And the first method means the open loop step input response method, determine the analog and the digital PID transfer functions. And the following forms we will use for our PID controller. So this is the analog form, so I call it A. So you see the KB, you see the TI, and you see also the TD. And for the digital, I call it D. In this case, of course, in the Z domain or in the Laplace domain, S domain, you see the small letter K sub P. There's a Ki, small ki, and small kd. So there are three different parameters here and three different parameters there. So how do we work with that? Okay, first we start with the analog PID controller design. So we need the delay time, the time constant, and the DC gain as said. And we will also draw a tangent line on the inflection point, what we call for this unit step response. So let's do that. So we have this transfer function. So what I do is I apply actually a unit step input and look at the response. You see actually this is already having 3 poles which are real, and the DC gain here is also 1. We will see that shortly what it all means. So, and we will then look at a tangent line, and it will be then used to determine the delay time and also the time constant. You see here the actual response of this in the simulator. You see here the response going actually as an S shape, as we have discussed in the general form for the Ziegler Nichols method. Now, what does it mean by inflection point? Well, you see here the slope, it is almost 0, and then increasing at actually a point where it is maximum. That point is where you see the inflection, and then it is again decreasing. So that point where you have the maximum slope, that's what we call the inflection point. So that point, I give it here with a dot, pink dot, and on that point I will make a tangent line. So this is the inflection point, and I will make a tangent line. Now from this tangent line, I will now determine the required delay time, time constant, and the DC gain. So this is what I do here. You see that from start to that point where the intersection of this red line and this x-axis, and there's also this intersection from the red line here up to the all the way here, which is then at 0.9. So this is our 0.0 to 0.12, or approximately 0.12, so I just read off here, and this is 0.9. And this distance is L, and this distance is T. So this is then 0.12 seconds, and this is 0.9 minus 0.12 is 0.78. So delay time, as said, 0.12 seconds. So that's actually now determined from the unit step response. Time constant 0.87, and we have a gain, DC gain of 1. Why? Because you apply 1, and you get also 1. So if this, for example, was 7, or KDC was 7, because you start with a unit step input. So if you want, for example, that's also what I said, if you do not have this and you apply on an unknown black box your unit step input and you get this response, then your planned transfer function will be then given by this, where you see the lag, which is our time delay, and our first order system approximation in cascade form, where you see also the 3 parameters which is determined. So we can now substitute this here. You can say KDC is 1, L is 0.12, that's actually what you see here in the exponent, and also this 1 plus 0.78. Now we can rewrite this so we can see also the pole clearly. So what you do actually is you divide the numerator and denominator by this 0.78, and you get here actually 1.28. So your pole is at minus 1.28 for the first order system. So this is now practically your model if you do not have the transfer function. All right, so the step 3 is now we will determine the analog PID controller transfer function from the Ziegler Nichols table. So only what we have done is so far the L, the T, and the KDC from the unit step response. Okay, getting back, this is our diagram or the response we had discussed, and also determined the time delay, the time constant, and also the DC gain. Now we need to also look at how we can determine the KP, TI, and TD for our analog PID controller. This is again this table for the Ziegler Nichols for analog PID controller, and this is the part, this is the row where we need. So we see the Kp determined by this expression, Ti by this expression, and Td by this expression. So that's actually what we need to do. So we will look at the expressions here and look also what we have found from our unit step response and then determine the parameters. Now the Kp is 1.2, that's shown here, and then T over L kdc. So T is known, L and the kdc is known, so we could just substitute that. 0.78, 0.12 and 1, you get here 7.8 exactly. Now Ti is 2 times our delay time, which is then 2 times 0.12, will be then 0.24 seconds. And Td is our half of that, so this actually is 0.5 times L, that is actually then here 0.06 seconds. So we have now the parameters all together here, and now we can set up our analog PID controller transfer function as shown here. So Kp, Ti and Td. Here we go. So 7.8 here, 0.24 here, and 0.06 here. So all from these calculations. You can also convert this expression in a form where you see the fraction and clearly also the pole at the origin. And also we have a double zero at minus here 8.333 approximately. So a pole at the origin, you see that, and there's a double zero at minus 8.333. All right. Okay. Now we have determined our analog PID controller. This is of course our first try, so we will see if this is really giving a nice response. So that's actually what we're going to do now. So we will look at the transit response and the simulations, but now using the closed loop transfer function. So here the unit step response of the closed loop transfer function, I call this TA1 with the original design, which is this one, analog PID controller. And this is now the configuration. We have the plant, this one, PID controller we just designed, this one, and you have here the unit step input R, and this is the response Y. And you see here the blue, which is a response. Now we see here some things here. Let's first look at the closed loop transfer functions. So TA1 is then the output divided by the input, and that's then given by the Mason's gain rule, so A times G divided by 1 plus the loop, which is then again the A times G in this case, because the loop is a 1. And if you now do the math here, of course it's a little bit tedious, you get actually this result. So I did this actually using MATLAB, and this is the expression you get. You actually have here a fourth order expression. Well, what actually is interesting, not this transfer function, but interesting is what is the performance. Well, this is the unit step response produced by MATLAB, and you see here the overshoot, the settling time, and also the final value is given. So if I now summarize this here, the overshoot is 73.5%, not quite high. Settling time is almost 5.5 seconds, and the final value is 1. Well, we apply 1 as a unit step input, and we reach 1, so there is 0 steady state error. That's of course nice for position error and position control systems. But settling time is quite large, and also the overshoot is huge here. So we can say, well, we have a system, it is stable, but it is very slow and also very large overshoot. So what can we do about that? That's exactly what I discussed in the beginning. We might have, of course, a PID controller that might do the job, but it is, of course, not really perfect. So we need to have this tuned. So we can tune this analog PID controller using the methods we will discuss now. So we can, of course, leave it like that. You can say, well, there are no specifications on overshoot or settling time. So why do you bother about that? Well, we can improve it, we know. So we can make this better. You can lower this overshoot, you can increase, or reduce the settling time, you can make it better. So let's try that, and it will also make the system response much better. So that's step 4. So we will now do the tuning of the analog PID controller we have designed for more and better performance. All right, again, getting back, so we will now do the tuning, and this is now the original transfer function we just determined, and this was the transfer function in the form where you see the zeros and the pole clearly. Now to make the system faster and also to reduce the overshoot, so faster meaning the settling time is shorter and also the rise time is shorter, we will move this double zero, which we have at minus 8.333, to arbitrary value. I just do that really by some experience, of course. I put it here at minus 3, but you can also put it at minus 4. So I will just place it a little bit closer to the vertical axis. In this case, I also want to keep this Kp I have here designed in the original form as 7.8. That is done actually to keep the speed as close as to a small value. That's actually the purpose. So we'll see that now, how we can do that. And in order to do that, I will look actually the expression A2, a new one, so not A, but A2. So you can also call this A1, for example. This is the A2. In this case, you see here the S plus 8.333 squared is now changed to S plus 3 squared divided by S. And here in front of it, I should now know what then the parameter should be in order to get again to this 7.8. So how do I do that? What I do is the following. This X is to be determined in order to keep this Kp to 7.8. That is actually my objective. So I will work out this parenthesis first, so that it will be S squared plus 6S plus 9. That's actually this parentheses work out. And we have this expression. Now if I now work it out further, so I see here that 6S over S is 6. 9 over S is just 9 over S. And here's S squared over S is actually pure the derivative part S. Now we can continue. We can also say let's put this in a form where you see here the 1 plus etc. because that's also the form here. There you see directly what the Kp is. That's why I'm doing that. So I just place this 6 outside the parentheses. Then I have to divide this 9 also by 6. Also this 1 by 6 or 1 over 6. Well, you see here directly the form I actually want. And this 6x is actually the Kp I want, which is then 7.8. So in order to have this 6x to be 7.8, I have to make this expression. So I say x is equal to Kp over 6, and that would be then here 1.3. So that means in front of this must be 1.3. So if I make this in MATLAB as a new transfer function expression, this one will be then 1.3, and this is 3. Well, you see also this now. A2 is then 1.3 times this expression where you see the double zero at minus 3 instead of minus 8.333. But you can also work it out here, and then you again get your 7.8 as we of course designed for, and now also 1 plus 1.5 over S plus 1 over 6 times S. Now what do you recognize here? Well, this Ti is 1 over Ti, which is actually this 1.5, which means then Ti is itself then 1 over this 1.5, which is 2/3. So the new parameter for an analog PID controller is then Kp, that's exact same as before, so 7.8. But Ti is then 2/3 because that is 1 over the 1.5. And the Td is just that what we see as a coefficient in front of the S, which is then 1 over 6 seconds. So we get the new parameters for our tuned analog PID controller. So let's now look at the transfer function again, and also the comparison between the original A and the tuned one A2. This is the Kp, they are exact same, but Ti is now increased from 0.12 to 0.6667, which is then 2/3. Td also increased from 0.06 to 1 over 6, which is 0.1667. So we have changed our transfer function, also our Ti and Td, looking at these steps. Okay, now we will simulate this circuit using the tuned analog PID controller. So we will again look at the closed loop system. And this is now our tuned version of the analog PID controller. Again, I show you the blue line, which is the response of the system where you have the original PID controller we have designed, which is the A, and now the TA2, which is the closed loop system transfer function, where we have the A2 instead of A. So the red one is that. So what do you see? Now the closed loop transfer function for the new one, where you see the A2, tuned analog PID controller, is then given in the same formula. You see exact same form here, and now you see here again the fourth order transfer function. Now the clear difference is that we have now here 2 poles which are real instead of actually 4 poles which are actually here in this case a complex which has a complex part. So we have 2 poles here, and it will of course determine, also change the performance. What do we see here? Now let's label them. This red one has a overshoot here 20.3%. The settling time is approximately 0.6, less than 0.6 seconds, and the final value is also 1 as before. So the performance, in summary, 20.3%. As overshoot, settling time almost 0.6 seconds, and the final value is again 1. So the comparison is here. Now, if we look at the performance, overshoot, settling time, and the final value, original PID controller, so the system with the original PID controller was this, And our tuned version, just by shifting this 0 and then adjusting, of course, this value such that the KP is still 7.8, actually reduce your overshoot by more than 3 times. And the settling time is actually reduced by almost 10 times here. You see that, so it's a huge improvement. And final value stayed at 1. So the red performance or the curve here is much better than the blue one. So that's also the reason for going for a tuning step instead of leaving this blue initial design PID controller. Okay, so the better performance, but the question is, can we make it better? Probably yes. So we will always search for a better performance, and if it's not possible, we just leave it here and then we accept actually the result. Again, there is no specification here like the overshoot or settling time, so that's why actually what I'm doing is now looking at better performance as much as I can do, because you can also say let's stop here because it's already good enough because there is no specification at all. That's true, but I will try to make it better, even better, and also show you how I can do that. Okay, so further tuning of the PID controller, that's actually my purpose now, and that is what I also will show you to make it even better. So you see here now the unit step response of the closed-loop systems. Again, TA2 as we have it before, that's the blue one now. And TA3 is another tuned analog PID control, but now we have A3, a new version. That's the red one. You see already this is actually a little bit slower, as it has less overshoot. It also has a little bit larger, or actually larger, almost 2 times larger settling time. So the original was this. This is actually our first version of our analog PID controller. This is our tuned version we just did. And in order to reduce now the overshoot even further, we can adjust this 1.3 to some value which will maybe do the job better. And that is actually what I did by, of course, some trial and error in MATLAB, and I get to approximately 0.61 here. And I will reduce the overshoot significantly. You see that actually here, 20.3 went all the way to 1%. But the settling time will increase almost by a factor of 2. So this is actually the trade-off you need to make. If you say the overshoot is actually predominantly what we actually want to reduce, then this is of course a very nice result. So the tuned analog PID controller, again the same 0, double 0 at -3, but just this 1.3 look at the 0.61 approximately. So again, our original PID controller system, our tuned version we have done, and now this further tuned version, so this is actually A3, the third version. You see actually the overshoot is actually now just 1%, so almost no overshoot. Settling time, yes, it has increased from the 0.6 to 1.1, but still much faster than the 5.55 seconds as we have it in the original case. And all the versions has a final value of 1, so there is 0 steady state error. So you might say, well, this is still not the version I want, because this 1.1 second is much larger than the 0.6 seconds. I want to further increase that. That can be done really. So you can actually play around with this one by looking at this transfer function, maybe change the 0, maybe again change the gain here, and then come up with a maybe much better performance. In this case, I just show you how you can tune that as an example. This is not an exact science, but of course give you an estimation what you can do, and also where you can change the parameters in order to improve that. If you increase it, for example, to 1.3 to let's say 5, you'll definitely have a larger overshoot, but your rise time will also it will be shorter, so you can also rise in a much shorter time, if that is of course a very important parameter for your performance. So this is a much better performance, and you might say also let's keep this as a final design, and we are happy with this. All right. Now, step 5, we will now do the physical realization of this analog PID control we have just designed, which is A3, the final one. So let's see how we do that. So we will use this tuned analog PID controller, the third version A3, and for that we will use the components. So this is the this is the circuit. You see the operation amplifier and the 2 resistors and 2 capacitors, and that will be then used in order to realize this transfer function. You actually see here an inverting amplifier configuration, the input voltage and the output voltage, and what I will do is I will designate this as ZI, which is our input impedance, and Z feedback, which is our ZF. Well, the transfer function here is, I call it H, which is the VO, output voltage, divided by the input voltage, is the ZF divided by the ZI. Well, there's also a minus sign here, so officially I also need to invert this, but let's ignore that for the moment, and you can always invert that using an additional inverting amplifier or change the wiring in your system. That will be then of course fixed quite easily. So let's now focus on the ZF and ZI and just ignore this minus sign for the moment. So ZI is the parallel combination of this R1 and the reactance of the C1, which is then this. So the reactance is in the Laplace domain 1 over the SC1. And if you now convert that, will be then this times that divided by the summation. That's actually what you see here. And that will result in this expression. Now ZF is just the series combination, similar, and now using the C2 and the R2, and that's shown here. And now we have the blue and the red expression, which is actually shown here. If I now put it here and then also change that expression, you see already here the S in the denominator and also the 2 parts for the zeros in the numerator. Now we can change that and massage it a little bit, and you get here this expression where you take out this R2 and C2 out, and also the R1 and C1 out. That will be then 1 over R1 and C1. And 1 over R2 and C2 here. But I will lose a C2 here, and I will also lose the R1 here, so I will get R2 C1 in front. That's here shown here, and also here the 0 at that location and another 0 here, and a pole at the origin. So we have 2 poles actually for given by 1 over R1 C1 and 1 over R2 C2. That's actually the expression for the components, but we have a double 0. That means 1 over R1 C1 is equal to 1 over R2 C2. That has to be because I have here S plus 3 times S plus 3 over S. So I cannot make this different. So we have this. 1 over R1 C1 is equal to 1 over R2 C2 is 3. Or R1 times R2, I1 times C1 is equal to R2 times C2 is equal to 1 over 3. So the product of the components must be done also 3. That's actually 1 over 3, that's actually shown here. And we also have an additional expression, which is then R3 times C1, which is actually what we see in front of it. That's actually the 0.609, etc. That's actually shown here. So we actually have 3 equations. R1 C1 is equal to 1/3, R2 C2 is equal to 1/3, and this R2 C1 is equal to 0.60932. But we have 4 unknowns, so we have 3 equations, 4 unknowns, so we have to select one. So we will select the C1 in this case, so we always, most of the time, select the capacitor because that's not really found easily compared to the resistors. So I will take here the 1 microfarad for the C1, really arbitrary. You can also take the C2, it doesn't matter. You can also take the resistors, it doesn't matter really. So I will take the capacitor here. Now from there I see here, I can now calculate this R2 because I can now make this expression here. That's actually shown here. So 0.60932 divided by the C1 I have just selected. And that will give me here 609.32 kilo ohms. So that's R2. R1, now we're looking at this expression. You can now calculate that because the C1 is also known because we have selected that. So we can say 1 over 3 times 10 to the power minus 6, which is the 1 microfarads, and that will then 333.33 kilo ohms. And how about C2? Well, that is then again using this expression where you see that. So C2 is 1 over 3 times R2. R2 is just calculated here. So substitute that and you will get here 547.06 nanofarads. So we have now all the 4 components by selecting one of the components here. So in summary, we have the components here, R1, R2, C1, C2, and the circuit here in the simulator, which is the TINA TI SPI simulations. So you see here the input VI, output VO. We have the operation amplifier in this case, just as pure ideal, R1, C1, R2, and C2. Well, you might say, where is this R3 coming from? In the simulator, I have to make a DC pad for my operation amplifier, otherwise it will not simulate. So what I do, of course, we have here an open loop, not a resistor or something. What I put here is a 1 tera ohm, which is a very large resistor. So instead of keeping this really open, perfectly open, I have put here a very, very large resistor. So it is not really affecting actually our performance, but still will run the simulator. Otherwise, the simulator will complain about that. It will give you an error. So that's actually how you can solve that problem. All right, let's also look at the simulation results now, the frequency response, the Bode plot for our designed circuit. Now you see here the body plot, just the gain. You see here the gain. You see the frequency running from 1 millihertz all the way to 1 kilohertz. It starts actually with a very, let's say, steep line down, and then reaches a minimum, and then going again up. So what do we see here? Now let's first present our transfer function, and this is the circuit. This is the minimum gain we reach. It's 11.26 dB. It's not actually an important parameter. This is the important parameter because you see this happening at the frequency 0.47737 Hertz. That's double zero, by the way, because if you convert this Hertz into radians, that is 3 radians per second, which is this one. So we see here, also from the body plot, that it is indeed correct. So what we see is indeed these 3 radians per second. What you also see is the first part that is actually nice to see. This gain of 52.8 dB is happening at 2 millihertz. And if you go 10 times larger in the frequency, which is then 1 decade up, the gain drops by 20 dB, which is then 32.8 dB, which is a characteristic of an first order integrator, and that's actually because of this the S here. And since the zero is coming to the picture, it will actually we have actually double zero here, and it also makes again the system first order differentiator, and which is actually going up by also now 20 dB per decade up. So this is minus 20 dB per decade slope, and this is a plus 20 dB per decade per slope, because you see that also here 31.7 dB at 10 Hertz, 51.7 dB at 100 Hertz, so 10 times larger in frequency. So you see this is really also what we see that from our transfer function, and our zero location is correct. This is actually a very important parameter here. Okay, now we will do the job where we see the digital PID controller transfer function, as we have done it also for analog, now using also the Ziegler Nichols table. Alright, so we will now design the digital PID controller using the Ziegler Nichols tables. First we will bring up our open loop unit step response of the plant. We have discussed this S-shaped response of our plant, and we have determined from there the L, the T and the KDC as we have done it before. So these are the values, and we will use this. In this case the table has adapted a little bit, because you see here now the L plus TS, and TS is here the sampling period in seconds, so the sample frequency will then 1 over this TS. So this L here will be replaced by L plus TS. So everywhere where you see an L, it will be replaced by L plus TS. That means effectively your delay will be a little bit larger, because the TS is always larger than 0. And also here, also there, so everywhere where we see an L, that is the only change. The rest is actually the same. So here we will look at the PID controller parameters, again the KP, TI and TD. So those are of course different now, will be different. So we'll now again calculate that just by selecting a sampling period here for this digital PID controller. In this case we will take the TS of 0.1 seconds, so 100 milliseconds. It means your sampling frequency will be 10 Hertz. Of course not that fast. We will see shortly what it all means, what kind of effect also the sampling frequency has on the controller design. So from the table of the Ziegler Nichols for the digital PID controller, we will see the KP will be then 1.2 times T over this. So this is actually this exact same as before, just this TS addition. That will of course make this a little bit smaller. In this case not 7.8 but 4.255. You see here the 0.1 we have selected. TI, new TI is now here 2 times in parentheses L plus TS from here, and that will be then here as 0.44 seconds, and TD from this part you get here now 0.11 seconds. So now this is done. By the way, we need to look at the small letter KP, small letter KI and small letter KD. So not these 3 parameters. So it's not possible that you just put this in here. And for that we need to do another step, that is actually going from these parameters to these 3 parameters. That's actually done here. So the KP, small letter KP, is exactly the capital letter KP. So just 4.255, that's done. KI is the sample period divided by the TI, which is calculated. So that's actually 0.1 over 0.44 is 0.227. And KD is the TD we just calculated divided by the sampling period, in this case 1.1. So taking this all together in this expression, now the digital PID controller transfer function will be like so. So you see here the Kp, Ki and Kd in here. Now we will now use this in the design to look at the performance now in the Z domain. So this is actually now in the discrete time system. Okay, now we will bring it up here and now look at the situation. First, what we do is we will put this transfer function, the digital PID controller transfer function, in a form that is more suitable for our analysis. So what we do effectively is bring actually these three terms in one fraction by having the same denominator. So this part we will multiply by z times z minus 1, and this one just by z, so you get actually z squared here, and this one we multiply by z minus 1, so you get actually z minus 1 in the quantity squared. Why do we do that? Again, as said, we like to have one fraction. That's actually the purpose here. Now the next step is then shown here, so you see actually this part plus the 0.227 z squared, etc., all divided by z times z minus 1. Now we can now work out the parentheses, a couple of steps of course in between, and now at some point you can make this in a form that you have this 9.902 and then times z minus 0.6875 in a quantity squared. So you see actually the 0, double 0, and also the pole, and also the pole at the origin, and also pole at 1. Of course the z-plane and the s-plane are different, so it doesn't mean that this is an unstable system, because the z of a pole of 1 looks like an unstable, but it's actually for z domain not unstable. Okay, now the closed loop system, how it works. Well, we have discussed this in great detail in a separate video about the digital controller designs, where you see actually the z domain expressions and also the closed loop systems there. Here also we will do that a little bit briefly. So we have actually this diagram we will use. You see here the RS in the Laplace domain. Then we have the summation part here. This is the output Y, so it is exact same as before. Now we get a sample in front of this PID controller, which is our DZ, and also after that. That is actually sampling at the sampling period of TS we have selected as 0.1 second, but it can be of course anything else. And then we need to hold that sample because this should be sampled. So you sample something and then you need to hold it and then process that to the plant. And that holding has a transfer function which is not derived here, but that is given by this expression, where you see again this TS, which is determined by your sampling period. And the plant is of course also in cascade in this system. So the holding operation, which is given by GH here, sub h, is this 1 minus e to the power minus STS, which is this sampling period over S. And this is, by the way, called the zero order hold. Why it's called the zero order hold? Because if you have a sample, it holds that and it makes actually a horizontal line, which is actually a zero order, where there's no slope in it. You have also the first order hold and also other hold operations, which are more complex. This is most often used, so that's also what we have here. And this is the transfer function for our plant. What we now do is we will take this together in cascade. So the sample, hold, and the plant together, transfer function will be then G sub S, just to discriminate that from the G, so not to confuse that, is then GH times G. So the plant transfer function times the zero order hold transfer function. And that's shown here, you see that. And what I do is I will now make it a little bit more convenient, written like 1 minus this e to the power minus STS in front, and then S here will be then in the denominator of that one. There will be now a fourth order system here, and this is a part we will now use. Now we need to of course now go to the Z domain, so we need to make a Z transformation of this sample, hold, and plant transfer function, what's called the G sub S. How to do that? Well, you need to make the Z transformation, so Z and then take the transform of this one. Now that can be done like so, and we can recognize that e to the power minus STS can be also written like z to the power minus 1. That is of course the definition of the Z transform, so that can be replaced. And since this is only a part or a parameter of Z, we can take it out because we need to transform the S parameters into Z parameters. So this is Z, so we can take it out. And now the only Z transform we need to apply is on this 160 over this S times S plus 4 times S plus 5 times S plus 8. Well, this is again a very tedious operation. You need to do partial fraction expansion, etc. I have done that in a separate video. I will also place the links to that. But if you do that, also can verify that by MATLAB, you get this expression where you see here the G of Z. Now, this is the transfer function we need, which will be used in the performance analysis of our digital PID controller. Now let's bring everything here, and this is the digital PID controller transfer function we have designed, and this is now the sample, hold, and the plant transfer function all together in the Z domain, and now we will move on. Well, the next step is now look at the closed loop transfer function as we have done it for the analog system. So TD is now our closed loop transfer function, the Z domain, and we put here a 1 because we might need to tune the system, and this of course all in the Z domain. So you see here Y of Z over RZ, that's actually the complete transfer function in the Z domain. That's DZ times the GZ and over 1 plus again the loop, which is exact same in this case because there is a unity gain feedback. Well, if you work it out, it's of course a little bit tedious. I will leave the details out, but it's actually this one and this one in the expression, and then you work it out after several steps and you get this expression. You see actually here 1, 2, 3, another one here second order, so you get actually here fifth order closed loop transfer function. Okay, now we will look at the simulation results, which are done for the closed loop system with the original analog PID controller and this original digital PID controller. So we will make a comparison now between the analog and the digital domain using our controllers. So this is the initial controller we have designed, the first version of the analog PID controllers, and is also the first version of the digital PID controller. And these are now the transfer functions. So TA1 is for the analog closed loop and TD1 is for the digital closed loop. So the red one is for the digital and the blue one is for the analog. You see actually here the red one has a little bit larger overshoot, not much larger actually, and it's also much slower. So this again the transfer function and also the diagram. You see here the DZ and sampling period is of 0.1 second. And here the performance. So looking at the closed loop transfer function using our original analog PID, we had an overshoot of 73.5%. We know that we have reduced this to 1%, but looking at just original PID controllers in analog and a digital domain to compare that clearly, you see actually that the DZ, which is our original digital PID controller, has almost 82% overshoot, so much larger, and it's also much slower, so almost 2 times slower. So you see it is actually having a less performance, so the performance is not bad, not as best as actually in the analog domain, but we can make it better. How? By actually reducing this TS. Well, there is a limitation here, so we will also look at that more carefully. Also the final value is 1, so that's actually for both of them the same. Okay, how about that? So that's actually our next step. So we would like to see if we can maybe make it better. Now you see here again our blue, which is our our analog system. The red one is our original digital system with the original digital PID, which actually has a TS of 0.1 second, and TD2 is a digital PID controller just by changing the sampling period, which is now in this case not 0.1 but 0.01 seconds. So it is 10 times faster in sampling, so it is 100 Hertz. That one is the green one. It's actually a little bit hard to see. So it looks almost actually analog, but it's actually discretized. When you now again look at the transfer functions, this is actually for the sampling period for that, and this is for the transfer function D2 when you change the sampling. You see actually everything is changing. It's not just the sampling period and the transfer function will stay the same. That will of course change, that will depend on that. And this is now the sampling of 0.01 second. This is all done, by the way, this transfer function in MATLAB. Now here we have the performance, again overshoot set link time and the final value. This is the original analog PID controlled system. Here we have the original digital PID where we have the 0.1 second, and now this is changed to a 0.01 second. What has now change here in the performance? Well, we see here that the overshoot has reduced. You see that it's from 81.9 to 72.6. It's actually also smaller than for the analog system. The settling time is also reduced, so much smaller than before for the digital system, also smaller than analog, and the final values are all 1. So you might say, well, it is actually getting better by digitizing this and also taking a sampling period which is smaller than what we had before. So this might be making this performance of our closed-loop system in the digital domain much better if you choose a smaller value here, maybe 0.001. Why not that? Okay, let's see if that is really the case. So can we improve the digital PID controller by reducing the sampling period? Can we do that? Okay, that's a very good question. So we will check that now. So the digital PID controller performance as a function of the sample period TS. Well, I haven't, of course, shown you the details, but this is what I have analyzed in MATLAB, and also the plots. I looked at it. You see here the original analog PID controlled system with the AS, not the A3, but the first one. Digital PID controller we had designed originally, and where we have the sampling of 100 milliseconds or 0.1 second, now reduced by 10 times, again 10 times, 10 times. So we actually go up. Well, you see here the overshoot is of course first increased in the digital system and then reduced. But now at some point it is actually approaching this overshoot of the analog. So if you reduce that further, at this point 0.1 milliseconds to 100 microseconds, I get almost the same overshoot as the analog. Also the same settling time and also the same final value was always the case. But there's also interesting thing happening here when you even reduce this even further. So what happens now, we get actually an unstable system. So this one I have checked in MATLAB. When I choose a TS of 0.01 milliseconds, so 10 microseconds, your system is unstable. So that's actually a interesting thing to consider for systems which are discretized, that might produce an unstable system, which is not the case in the analog domain. That's actually a very interesting observation. So the conclusions again, reducing the sampling period, TS, will improve the performance, yes, but up to some minimum sampling period, so not necessarily going to very low values. The performance of the digital PID controller will approach then that of the analog PID controller by making the sampling period smaller, but of course again limited by this minimum value. By the way, I have not researched here what the minimum value might be, so it might be of course maybe 0.05 is also fine, we don't know, but you can see by reducing actually this TS will make actually your system unstable. So there's a limit here. And then reducing the TS even further has of course the consequence of an unstable system as said here. So we will of course not do that, so you have to be careful when you do the digital control design. Okay, let's now go to the step 7, which is our tuning of the digital PID controller for better performance, because we have some performance. We already see that we can also improve the performance by going to lower TS, but it's not really that promising, so we need to make it more actually better. So it's actually the step 7 now. So we will now go to the tuning of the original design PID controller. So that's actually the original digital PID controller, and we will now actually make it like so. So what we have done is the following. We only have changed this. So the Z double zeros are exact same and the poles are exact same. So 9.902 has changed to 2.577. Again, this is done in MATLAB by fine-tuning. So that is actually the operation there. So we can make that faster, the system, and also reduce the overshoot by adjusting or reducing actually the gain. Why do I actually reduce it? Why do not increase that? Well, I already have very large overshoot, so increasing that will make it even larger. So that will of course create more power in the system. So I would like to dampen it a little bit. That's actually what I have done. So you see actually that the rise time is actually also larger for the red curve. So that's actually this new one. You see actually TD1 is the closed-loop transfer function for the original digital PID controlled system, and the TD2 is for this tuned digital PID control system. So the reducing this digital PID controller gain from the 9.902 up to 2.577, this is of course not a magic number, you can also maybe go to 2.6, just what I have done here by tuning. The overshoot has reduced drastically. So it actually goes from 81.9, so from 82% almost to almost 0.5%. So let's say almost 0% overshoot. That's actually what you have achieved here. Well, you also see that the settling time is also reduced a lot, because from 9.9 all the way to 0.7 seconds. So here is the summary. You see that. So we have achieved this, by the way, the same sampling period. So TS is still 0.1 second, but you see how faster and how low that overshoot is. So this is actually a very good performance here. So we will go for that. And how I did that, I will also describe that here. What we can use in MATLAB is the Control System Designer app, where you see the root locus, the Bode plot, and the unit step response all in one picture. So on the left side, I have only the root locus now, and the right side is the unit step response. So the change here in the pole location, so you can grab actually this pole and then move it up or down. That can be done in MATLAB. This will then respond automatically on that response, and you can see how fast that goes. And that is actually the operation I have done in MATLAB, and then looked at the position where I have a nice overshoot and a very small settling time. And then I stopped there and then exported the data and get my tuned digital PID controller. So I will also show you that now in between, so how you can do that in MATLAB. So we'll now jump to MATLAB. So we are in MATLAB, and you can see here the script. Actually here we have written, you see here the definitions of the Laplace and the Z domain parameters, the original plant, and the parameters we have discussed. Now what we do is first we will run this. So we will actually run the script, and what we then need to do is, in order to tune this, because that was the objective for this discussion, go to the apps, and you can go to here, you can also launch this, to Control System Designer app. And if you click on this, it will take some time. It will bring up the application where you can insert your controls, because you see here the A1, which is our original analog PID controller. We have here also the A2, which is our tuned version, by actually selecting these values we have discussed also there. And we have also this plant again for this Z domain operation, where you see the TS, the sampling period, etc. And now you see here the D1, which is our original PID controller in the digital domain. So you see here the application is now up. And this is actually the first picture you get if you open the Control System Designer app. You see here the Bode plot, here the root locus, and here the unit step response. I will not use the Bode plot, so I will close that. I will also collapse this part so you get more space here. And also what I do is I grab this and put it here to the left side. So I have left the root locus and right the unit step response, as we have seen in the slide. Now I will also put the grid, so I like that to see actually clearly what's happening. Then what you need to do is, you can also make this a little bit larger. We need to import here in the architecture our transfer functions for our plant. Let me make this a little bit smaller so you can see what's actually here, or maybe go that way with my script. Now here's again the Control System Designer, and on the right side we have our script. Now if you look at the architecture, so click on the architecture, you get actually this one where you see different architectures. So this is the simple one we have now, the controller here, the plant here. There is no block here in the feedback, so this is H, which will be just one. Pre-amplifier or pre-filter F is also one, but you have also different configurations, by the way. You have this one where the controller is in the feedback, the pre-filter like so, or two controllers, what we call also the 2 degree of freedom, more complex and more performance available there. But we will go for that, that's actually what we have. Okay, the C here is our digital PID controller, or original. So that's what we hear D1. You can also do import, but you can also type it in, it's much faster. F is 1. The H is also 1. But how about this G? Well, G is, of course, in the analog domain, G this one, but of course we will now do it in the Z domain, which is discrete time. We have to look at the GZ. So that's actually what you need to type in here. So don't forget that. And when you now do OK, it will now update the architecture. And then you will see here, the left side is our root locus plot, and the right side is our unit step response. It says unit step response, but it's actually unit step. I will increase this, so make it larger. So you actually see here now this complete picture. And you also see here the performance on the right side. So you can click on the right mouse click, steady state value. Steady state value is always 1 here, but let me first do the overshoot. See 81.9% as we have before, and also here this settling time on 9.9. Now I can grab this with my hand here, which is this purple dots. Those are the close to poles. The circles are here, all the zeros, they will not move. The poles will be moving. And if I grab this, I can go up and down. You can also see if you zoom in, this is of course the part, I will zoom in a little bit. You can see better what's going on. This circle is actually a unit circle. You see actually from here, the distance is 1, going up is 1, left is 1. So that's actually the region where we have a stable system. If you go outside that, you will have an unstable system. I can also show you that. So if you go and grab this pole and go out, you can see what happens. So you see actually this is going and blow ups, and then it's unstable. So I will go back here and now again enter the domain of the safety. You see again here the overshoot and settling time, of course now for different part. What we now need to do is we go down, 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 and that's also what I have done for my controller. And at the point I get my overshoot and my settling time to a value I'm okay with it. That's actually what I have done. So you see here I have now reached here 1.4 seconds as my settling time and the 5.8% for overshoot. I can make it even better. Let me go a little bit up to show you actually something else. This is the settling time. This overshoot is almost 0. You see that, and the settling time is here. Let's say 0.8 seconds. If I go a little bit up to see the exact performance I had described in the slide presentation, so this is actually what I had. See, not really that exactly, but it's 0.727. So if I go a little bit larger or smaller, I mean, so I have to zoom in to make it a little bit better. So go down, you see that, go down, and this is approximately what I had. It was something like so. So what I now need to do is, so what's now the control we have designed? We don't know. So I can also do the full view. That can be done by going to the root locus control systems tab and then do the export. So I will do exporting. And what do I export? Well, I do export now the designed, so the current controller. So I will select this because that's the model. I can also place that as, let's say, a model I want to name it. So I can say detuned. Yeah, I could just name it a different name. So that will be then exported like so. So I will now go back in the command window. Now we have called it detuned. Here we go. Underscore tuned. And that's actually the transfer function. You see here is 2.57 etc. So close to what we have, and also the 0 is there. And that's actually how you do it. So you can export that. And now you can use this transfer function for your design. Okay, now let's now jump back to our slide presentation and discuss this in detail further. So we are back in the slide presentation. So we have discussed how we can generate this plot and how we can tune this to get a better performance. All right, next step, step 8 is the physical realization and implementation of this digital PID controller. Well, we have now found our final digital PID controller by tuning in this Control System Designer app in MATLAB, and this was the transfer function. But how do we implement this? How do we do that? Again, this is our diagram for our sample time system. So we do first the implementation, and now we will specifically look at the part where you have the digital PID controller, only this part. So we have the sample and in front and at the end, and here we have the error in the Z domain, and we have also this X, which we call here the signal, the output of the digital PID controller, which is called this one. So the D2, which is our digital PID controller is then XZ over the EZ, which is the error signal, and that is actually this 2.577, etc. Well, we need to use this in order to determine the implementation. First, we look at the difference equation. Again, this X over E is then this one, so we can now do the expansion of this parentheses, so we actually work out the parentheses first. That's actually the first step, so Z squared minus the 2 times this one, Z, and then this one squared, you get actually this one, and now this is also Z squared minus Z. That's actually what you first do. The next one is actually taking this 2.577 here in the numerator, so every term here gets multiplied by this 2.577. Then what you do is you divide actually by the highest order, which is the Z squared, so you get actually here only 2.577, here Z to the power minus 1, and here Z to the power minus 2. And here it is 1, and then minus Z to the power minus 1. That's actually what you see here. Well, what do we do next? Well, what we do next is the cross multiplication. So you get actually this times the X is equal to this times the E. That's actually what you see here. Now I can also again work out the parentheses. That's actually what you see here. So X times 1, X times this one, and also for the E, you see actually everything is worked out. Now what do we see here? Now the Z to the power minus 1 means actually there is a delay of 1 sample, and Z to the power minus 2 means there is a delay of 2 samples, and also Z to the power minus 3, etc. So I can express now this X in terms of the other parameters, so I will replace this to the right side. You can see that here. And then I can determine here the implementation of this digital PID controller. Well, the next step is convert this to a sample time system, sample time signals. So the X and the E will be all small letters. You can see that small letters. So this XE, let me start with that one, will convert to a small letter X, and the Z will be then converted to NTS. And TS is again our sampling period. But if you have a Z to the power minus 1 in front of it, then you get actually a minus TS for that. And then also for the others, you get actually a similar one. If you have Z to the power minus 1 in front of it, you get actually minus TS. If you have Z to the power minus 2, you get it minus 2 TS. The coefficients will be exact same, so those are of course just linear coefficients, they will not change. So we need to now make this difference equation, implementation of that for our digital PID control. So this is the difference equation we will use. So let's bring it here and now move on. Now the realization of this situation, how that works, let's go continue with that one. We start first with the error signal, because that's actually where you have a sort of the input and the output is our X. So it goes in. We see here the error signal will have a coefficient, but also have a coefficient which is then delayed, and another coefficient which is then 2 times delayed. So we get actually 2 delays. So we have a TS which is delay, and then goes another one, and then goes. So it means this is necessarily what we need for our error signal in the sample form. And then that we have also an undelayed version, that's actually this 2.577. The other one is 1 delay, the other one is 2 delays. So that means we have here the coefficient 2.577, that's actually the gain here, or the coefficient here, the 3.543, and the final one is 1.218. And that will be then added together. That's actually here addition, so you get here plus, minus, plus. That's actually why you see here the plus, minus, the plus, and we get here the summation part. Well, it's not the full story, because we have also this one, which is the X, which is the 1 delayed version of the output. So we have the output, but also that needs to be delayed 1 sample period, and then also added to this block, and then together that will create this output. That's actually how you generate this discrete or difference equation into this realization diagram. Okay, now that's for that. Now in our final step, step 9, we will now make a comparison of our final designs for our analog and digital PID controllers. So we have found our tuned version, final versions of our analog and also the digital PID controllers. So our analog PID controller in the final form was A3. This was what we have discussed. And this is what we have discussed for the tuned digital PID controller, where it's sampling frequency of or sampling period of 0.1 second. Okay, here the unit step response for both closed-loop transfer functions. The red one is for the analog and the blue one is for the digital domain. So the TA3 is the closed-loop transfer function for the analog and the TD2 is for the digital. What do you see? Well, let's look at the performance. I also put here the extra performance rise time. So we have the overshoot, rise time, settling time, and the final value. Here the closed-loop system with the analog PID and the digital PID on the right column. Well, the overshoot here, if you look at it, is 1% for the analog, and for the digital this is 0.5 approximately, so 2 times smaller, so better. The rise time for the analog is 0.197 seconds, so almost 0.2 seconds. And for the digital it is 0.2 seconds. So it is 2 times slower in the rising. Now for the settling time, the analog is 1.1, but the digital is 0.7. It's also much faster, and the final value is 1 for both. So you can see here the overshoot is actually better in the digital domain. The settling time is also shorter in the digital domain, but the rise time is better in the analog domain. That's actually what you see here. Well, that was actually our complete video about the Ziegler Nichols tuning rules, tuning tables for the analog and the digital PID controllers. We have used the transfer function of the plant, and from there we have determined our S-shaped open loop unit step response, and from there we actually determined our parameters for our analog PID controller, and from there also the digital PID controller, and then moved on with the tuning. We also showed you the implementation of the physical implementation for the analog PID controller, and also the physical realization, the implementation and difference equations for the digital PID controls. And now the comparison as our final step. And I hope this gives you a better understanding how you can use this Ziegler Nichols method for tuning and designing your PID controllers. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. In order to grow our community and also this channel, please support us by sharing and liking these videos, and hopefully we can reach more people with your support. Thanks for your cooperation and see you next time in another video. Take care.